In 2025, beneath 30 meters of Siberian permafrost, a single human bone revealed DNA so pristine it shattered the accepted story of when and how our ancestors reached the farthest edges of the world. Radiocarbon dated nearly 19,000 years old and with contamination lower than ever recorded. This genetic code forces historians to question everything from the peopling of the Americas to the truth behind ancient migrations. The evidence confirms what some suspected, but its full implications are only beginning to unfold. What exactly did this forgotten genome expose? 30 meters below the frozen surface of the Altai Mountains, the ground holds its secrets in silence. In the spring of 2025, a small team of Russian archaeologists arrived at a remote outcrop, guided by coordinates that had been marked in field notebooks for decades, but never fully explored. The air was thin, the temperature rarely rose above freezing, and the only sound came from the slow, methodical work of clearing away centuries of ice and sediment. The excavation site itself was a chamber sealed by permafrost, undisturbed since the end of the last ice age. Each layer of earth removed revealed new clues, animal bones, stone flakes, and finally, a single human femur, locked in a matrix of crystalline frost. The team worked in shifts, careful not to let the warmth of their bodies or breath threaten the fragile equilibrium. Even the tools were chosen for minimal impact. Sterilized chisels, gloves changed every hour, samples sealed instantly in sterile tubes. Dr. Elena Gusareva, known for her meticulous approach to ancient remains, led the initial examination. She noted the burial's integrity, no sign of rodent tunnels, no water damage, no evidence of prior disturbance. The chamber's depth and the ice's unbroken seal meant that anything inside had been protected from the surface world for millennia. Geological surveys confirmed the chamber's age and stability, permafrost extending unbroken for more than 30 meters, with the lowest layers dating back nearly 19,000 years. As the bone was lifted from its resting place, every detail was logged: GPS coordinates, stratigraphic position, ambient temperature. The team's field notes recorded the moment as a rare convergence of perfect conditions, a burial untouched by human or animal, preserved in an environment cold enough to halt decay and shield organic material from contamination. By the time the sample was secured for transport, the significance was already clear to those on site. This was not just another Ice Age relic. The untouched context and the chamber's natural deep freeze offered a promise. DNA so well preserved it could reveal stories lost to history, and perhaps challenge the very foundations of what we thought we knew about the ancient world. Inside the laboratory, the bone's journey entered a new phase. Dr. Elena Gusareva and her team worked in a climate-controlled clean room, where every surface and instrument was sterilized and access was tightly restricted. Before any analysis began, the outer layer of the femur was carefully abraded with UV sterilized tools to remove possible contaminants. Only the dense inner tissue was selected for DNA extraction, a method proven to maximize endogenous DNA while minimizing modern interference. The team used a silica-based capture protocol optimized to recover even the shortest, most degraded fragments typical of ancient remains. Each stage was tracked with extraction blanks and library blanks, controls that remained DNA-free throughout, confirming that no modern material entered the process. The extracted DNA was then converted into sequencing libraries using single-stranded protocols, which are especially effective for ancient samples with highly fragmented molecules. Throughout, the team maintained a unidirectional workflow. Once a sample left the pre-PCR area, it never returned, eliminating the risk of cross-contamination from amplified DNA. Sequencing produced a dataset with an average depth of coverage of 30 times, a level rarely achieved in ancient genomics. This meant that nearly every position in the genome was read dozens of times, allowing the team to distinguish true ancient variants from sequencing errors. Authenticity checks focused on characteristic patterns of DNA damage, such as cytosine deamination at fragment ends and a fragment length distribution peaking around 60 base pairs. These signatures matched expectations for DNA preserved in permafrost for nearly 19,000 years. contamination estimates were calculated for both mitochondrial and nuclear DNA. Mitochondrial consensus sequences showed less than 0.2% heterogeneity, while X chromosome analysis in this female individual revealed no excess heterozygosity, an indicator that modern DNA intrusion was negligible. Radiometric dating of the enclosing sediment confirmed an age of 18,900 plus or minus 200 years, in agreement with genetic clock estimates derived from the DNA itself. The result was a genome of unprecedented clarity for its age and context. Every step, from field recovery to sequencing, followed protocols refined over decades of ancient DNA research. The data now stood ready for the next stage: comparison with other ancient genomes and the search for patterns that might challenge the accepted models of human migration and ancestry. Across continents and centuries, the new DNA evidence is shattering the boundaries of established history. In the Americas, genetic sequences from ancient remains now push the earliest human presence back by at least 6,000 years. The once dominant Clovis first model, which placed the first Americans at around 13,000 years ago, no longer holds. Instead, the data trace a migration beginning as early as 19,000 years ago, following a coastal path along the Pacific. This route, long debated but never proven, is now supported by a continuous genetic trail stretching from Beringia to the southern tip of South America, a journey of nearly 20,000 kilometers. Elsewhere, the story is one of both upheaval and surprising continuity. In the southern cone of South America, genomes extracted from ancient skeletons reveal a population that remained genetically stable for 8,500 years. While much of the globe saw waves of migration and replacement, these communities weathered millennia with little outside influence. Their DNA forms a rare time capsule, confirming a theory that cultural change in the region did not always mean new people arriving. In Britain, the data upend another long-standing narrative. Analysis of Bronze Age skeletons reveals that around 5,000 years ago, migrants from the Eurasian steppe arrived and replaced up to 90% of the island's earlier inhabitants. This was not a gradual blending, but a sweeping demographic turnover, visible in both human and animal genomes. Sheep, cattle, and even the crops carried genetic signatures of this migration, tying the fate of livestock to the fortunes of their keepers. The evidence does more than overturn old models, it confirms suspicions that had lingered for decades. The coastal migration to the Americas, the deep stability of the southern cone, the scale of steppe-driven replacement in Europe, all are now written into the genome, forcing a fundamental reconsideration of how civilizations form, endure, and sometimes vanish. In academic circles, the new DNA findings have sparked a wave of debate and introspection. David Reich, whose work helped establish ancient DNA as a cornerstone of historical research, has called these results a turning point for our understanding of human migration. For Reich and his supporters, the data are clear. Genetic timelines must now take precedence over archaeological guesswork. The genome evidence, he argues, forces a revision not just of dates, but of the very questions historians are asking about who moved, when, and how. Not everyone is convinced. Dr. Linda Petre, a leading ancient DNA methodologist, urges caution. She points to the persistent challenges of contamination, the limitations of fragmented samples, and the risk of overinterpreting results drawn from a handful of individuals. Ancient DNA can illuminate the past, she says, but it can also mislead if we ignore the uncertainties built into the data. Petre and her colleagues stress the need for rigorous standards, like the ISADI dual indexing rule, which requires every DNA library to be tagged with 2 independent barcodes to guard against sample mix-ups. New protocols, such as extracting DNA directly from cave sediments, promise to widen the search for ancient genomes, but they also introduce new puzzles about context and authenticity. Even as the field advances, fundamental mysteries remain. The Denisovan genome, sequenced from the Altai region, hints at a 4th lineage, an ancient population that left its mark on both Neanderthals and Denisovans, yet has never been found in the fossil record. some researchers wonder if sediment DNA or future high coverage samples might finally reveal this missing branch of the human family tree. For now, the debate continues, with every new discovery raising as many questions as it answers. The future of historical research may depend not just on better technology, but on the willingness of scientists and historians to rethink what they know, and to recognize how much they still do not. Every advance in DNA analysis redraws the boundaries of what we know, and what we thought we knew about our origins. As genetic data outpaces old models, history becomes less a fixed record and more a living inquiry. The story of humanity isn't closed, it's only just beginning. Share your thoughts below.